This video is on effusion and diffusion. So two words that sometimes are used interchangeably, but they mean different things. So diffusion is the mixing of two gases, whereas effusion is the passage of a gas through a small orifice in an evacuated container. So here I have a container that's split in half. This side is evacuated and this side has gas with the particles inside. And there's this little slit right here. Effusion is these gas particles coming through the slit into the new container or the evacuated side. So this is like a balloon when it deflates, when you haven't popped it. Those gas particles are slowly coming through the rubber of the balloon. They're escaping, or through the knot that you tied the balloon with, and that's effusion. So they're slowly passing through. Graham came along and he discovered his law of effusion or diffusion because they're both going to move at the same rates. So he said that the rate of effusion or diffusion of a gas is inversely proportional to the square roots of its molecular weight. So we've talked before about how big things move slower, and he said that in fact the rate at which they move is proportional to how big they are. So the rate effusion of gas 1 divided by the rate effusion gas 2 is equal to the inverse of, or is inversely related to the square root of the molar mass of gas 2 divided by the square root of the molar mass of gas 1. So notice that 1s are inverse to each other and 2s are as well. So if we were doing an example problem and we wanted to know, well, how much faster does hydrogen diffuse in helium? I know hydrogen's a smaller particle. It has a molar mass of 2 grams per mole. And helium's a larger particle with a molar mass of 4 grams per mole. So I want to know how much faster is hydrogen than helium. So I'm going to make hydrogen gas 1 because it's going to tell me a bigger number on the top versus the bottom. That's going to be how many times faster. If you go and do this and you get a decimal number, so 0 point something, that tells you that the slower one is that much slower than the bigger one. So you kind of have to watch where you put things. So if I'm looking for the rate of something faster than the other, I'm just going to say, well, this is my rate of one to the other, and I'm going to sub in for my molar masses. So the molar mass of my heavier one, which is my helium, is 4. And the molar mass for my lighter one, which is hydrogen, is 2. And when I take the square root of 4 divided by the square root of 2, I get 1.4. And so what this means, that's equal to the rate of hydrogen over the rate of helium. So I get 1.4 rate hydrogen over 1, because it's on the bottom, 1 rate of helium. And that means that hydrogen travels 1.4 times faster than helium. So I'd write that hydrogen travels or diffuses 1.4 times faster than helium. Okay. So this connects back to the kinetic molecular theory. We derived before that when we're finding out root mean squared, that is equal to the square root of 3RT over the molar mass. And so we can say that the rate of the gas is proportional to the rate being the root mean squared of the velocity, right? So how fast things are going, and how fast things are going, their kinetic energy has to do with the square root of 3RT over M1. And the 3RT is constant on the top and the bottom, so that cancels out of the equation. And so we're just left with the square root of molar mass 1 over the square root of molar mass 2. So it's kind of cool to see that these things come about. So they come about, actually this should be molar mass 2 over 1. So you want to fix that because it's 1 over molar mass 1 divided by 1 over molar mass 2, so that flips. Right, M2 goes on top versus M1 on the bottom. So it's kind of cool that we can see where this came from, that the rate equals to the inverse of my molar masses, based off of the kinetic molecular theory of how fast things travel, and that we can relate that back to the ideal gas law. And from there we come out with this.